Hi, everyone. Sorry about that. Welcome to the Isaac Sim live stream. If my audio is okay, can someone give me a thumbs up in the chat, please? Okay, there's a delay in the chat, but I'm hoping I'm okay now. My name is Buck Babbage. I'm one of the managers on the Isaac Sim team. I'm responsible for some of our motion generation efforts, especially in manipulation. So that's going to be the topic today. Okay, good. Audio is good now. So for anyone joining us for the first time, this is a series of live streams that we've started. I think this is the fifth or sixth one. And the idea is that different developers from the team are hosting each week. We're going to have a sort of a rotating cast of developers covering different topics. We're all novices at this. So if you notice any issues, let me know in the chat. This is meant to be pretty informal and interactive. So start thinking about your questions now. I thought we would start by talking about a motion generation algorithm called RMP flow, but we can branch out from there. So I'll let you know if you have a question that I'm not equipped to answer, and we can defer it to a future week or take it to Discord or the forums. So okay, I guess we can dive right in. So I decided to talk about RMP flow. So anyone who joined 2 weeks ago, Avi Rudish, who's one of the engineers on the team, gave an introduction to how to add a new robot to Isaac Sim. So that included creating a new extension from scratch using the extension templates that we've added to the most recent release of Isaac Sim. This is a nice way to create a brand new extension without having to copy one of the existing examples. So if you missed that, go back, watch the recording from 2 weeks ago. He walked everyone through how to add the robot, which includes adding a URDF file. It's a robot description file that's standard in the ROS community, and is also required by our motion generation algorithms. So he stepped through how to add that file, how to add a separate robot description YAML file, an RMP flow config file, and he went through the entire process. But of course, he didn't go into detail on what RMP flow is and why you might want to use it. So I was hoping to do that. I thought I'd tell you a little bit about what this method is, what are its strengths and limitations, what are some alternatives that are provided in Isaac Sim, and basically give you a little bit of an orientation to the documentation and cover a little bit of what you might not see in the documentation. So with that in mind, maybe let me start by motivating the problem a little bit. So this is a method for doing collision-aware motion generation, specifically for manipulators, for robot arms. That's the place where it's been deployed to date. There's no reason you couldn't apply these methods to other robotic systems, but for the most part, we've been focusing on manipulation. So let me share a video quickly. So Nathan Ratliff is a researcher and engineering director at NVIDIA, was one of the originators of this approach. So he and his collaborators several years ago originated this geometric approach to motion generation. And you can find talks of his online. I pulled up one just for some of the example videos that he included at the beginning of his talk. So if you search his name, these talks will give you more of the philosophy behind these approaches. I'll touch on that briefly, but I'm not going to go into depth. So just very quickly, maybe as I talk, I can play through some of these examples. So this is an ABB Yumi robot. I have to say this is a bit of a misleading example to start with because this robot has 2 arms. And currently, it's a bit awkward in the RMP flow implementation in Isaac Sim. It's a little awkward to deal with 2 arms. You have to basically treat them as 2 independent manipulators. And the collision avoidance between the two arms, so self-collision avoidance, is a bit awkward to manage. We're working on improving that, but I just wanted to mention that up front since we were showing the two-armed Yumi robot. So these are some examples. In this one, of course, there's much more going on than just the motion generation. This is an example where a depth camera is being used. Dexstream is the thing to Google, and there's been a follow-on to this work more recently. But motion generation obviously is an important piece of this, and especially for applications like this, it's important that it be reactive and be able to deal with obstacles and moving targets and so on. This is another nice little example, which is driven by RMP flow with the state machine sitting on top, but a lot of the nice smooth motion is coming completely from the RMP flow algorithm. And then this is just probably too many to watch all at the same time, but this is sort of a summary of some different examples. So I think one of the reasons we get questions about RMP flow so often, as you can see, some of these examples go back to 2019. And for example, this Leonardo demo, there's a version of this in Isaac Sim. And because this was one of the first motion generation techniques we added to Isaac Sim, many of the examples use it. And so it's natural, someone coming to Isaac Sim for the first time, they see all these examples using RMP flow, and it's natural to try to adapt them to their problem. And for many problems, it is, it might be the right answer. But I did want to mention, if we hop over to the Isaac Sim documentation, all of our motion generation tools live in a single extension called motion generation. One might argue that it is, it's maybe getting too big. There might be too much in here, but at least, if you're looking for something having to do with planning and control for robots, at least for manipulators, you can find that in the motion generation extension. And hopefully the font size isn't too small, but I'll just read down the left side. There's solvers for kinematics and inverse kinematics. There's a trajectory interface, which was added in the most recent release. This is actually pretty powerful. So this is I think maybe we'll want to have a whole separate live stream about this topic at some point. But if you've ever programmed an industrial arm, let's say using a teach pendant, the way that's done, or using the vendor scripting language, the way that's done is by specifying a series of moves, either in joint space or in task space. And so, you might say, okay, move the end effector to a certain position and orientation, then make a linear move in joint space, make an arc move, maybe keep, either slurping the orientation or keeping it the normal, having the orientation match the normal of the arc of the trajectory. So we do have an interface for building up a path out of a series of moves like this, and then automatically computing a time optimal trajectory given a set of acceleration limits, velocity limits, and jerk limits. So it'll produce a optimal time trajectory with smooth velocity, continuous acceleration, and bounded jerk. And so if you have a problem where you're just like an arm to do some task, and there are no dynamic obstacles, you just want to script out a task, you may want to look at this interface as opposed to using RMP flow. On the other hand, at the moment, we don't have much in the way of graphical, sort of visual tooling for building out these trajectories. That should come in the future. So RMP flow can be a convenient way to do this, even if you don't have to do obstacle avoidance. All right, let me go to the chat real quick. Great, someone, I'm guessing Edmar posted a link to the live stream from last time. And yes, I have too many books. So those were comments from the Twitch stream if you're watching on YouTube. So let's see where to begin. I guess I should start. I will stop sharing my screen for a moment and wave my arms at you for a minute and explain briefly what RMP flow is. Okay, so RMP is short for Riemannian motion policy. And we can unpack that starting from the end. So a policy in the control literature is basically a function that takes the current state of a system and produces an output or an action that specifies the desire that influences the evolution of the system, right? Along with the natural dynamics of the system. So that's a policy. A motion policy is a policy that has to do with motion, with getting a robot to move in this case. Okay, and then that brings us to Riemannian. And I should pause here to explain, give a little more background to explain where that comes from. So the specific kind of motion policy that we're interested in here is called an acceleration policy. And this is a policy where the output is acceleration in the configuration space of the robot. So, rather than outputting, for example, a desired position directly, it's outputting joint acceleration. And that's useful for a couple of reasons. One reason it might be a good idea is because generally the acceleration policy will be continuous, but even if it weren't, it would result in continuous velocities and smooth positions. So that's a nice property. So in general, we're going to be taking this acceleration, integrating it forward. So it'll it's given in discrete time. We're going to integrate it forward to get velocity and then position. And then normally we would control the robot using standard position or velocity control. Another reason it's nice is because it mimics the way physics works in the real world, right? So in our universe, all the laws of motion are given by second order differential equations, right? F equals ma, or you could write it as a equals f over m. And so let's say you have a ball flying through the air. Gravity is acting downward on the ball, so that's one force contribution. If there's air resistance, then you might also have drag on the ball that depends on velocity. And you could imagine others, right? You could add constraints. Maybe the ball is attached to an elastic string or something. You could add any number of contributions, and those forces all add up. And then you divide by the mass of the ball to get an acceleration. And then if you want to know the path of the ball, you integrate that forward twice, and that gives you the path in space. You could do the same thing with the rotational degrees of freedom of the ball. So that's how physics works in the real world. And the idea with these acceleration policies is to do something very similar, but the dynamics do not correspond to the actual physics. Instead, it corresponds to a sort of fake physics that we hand engineer to give the desired behavior, to give nice smooth trajectories that, for example, pull the end effector of the robot towards a target, that ensure that the various links of the robot avoid collision with any obstacles. Those obstacles might be dynamic. And an advantage of this approach is that it is extremely fast to evaluate. So we've been improving performance over time. The implementation of RMP flow currently provided in IsaacSim is way faster than it has to be. I mean, with tens of obstacles, you can run at tens of kilohertz, right? So way faster than it needs to be. That's on a single CPU thread. It's likely overhead will come in some of the Python interfacing and so on. But this is a very fast approach. And it's been shown to be a pretty powerful approach for certain kinds of problems, especially collaborative applications, which were the ones represented in those videos we were watching a moment ago. Okay, anything in the chat? Lots to learn here. Okay, yeah, so I'm not really going to go much deeper than that into the formalism. I think maybe we'll have a separate live stream. A colleague of mine can talk a little bit more in a few weeks about the full machinery here. But to understand what's going on, I guess I should say a few more things. Ultimately, a robot is controlled at the joints, right? You have actuators at the joints. And so in those examples I gave of, let's say, moving towards a target or avoiding obstacles, you can imagine that there are forces being applied at various points on the robot. And in general, those could be different spaces, right? So if you're avoiding collisions with an obstacle, at as you'll see, we represent our robots for the purpose of this algorithm as a set of collision spheres, right? So it's a rough approximation of the robot given by a set of collision spheres, often on the order of 50 to 100 collision spheres is good, depending on the application. And a given collision sphere with a given obstacle, you can think about this sort of one-dimensional space between that obstacle and the center of the collision sphere. And so that's defining a one-dimensional space along which a force is going to act. In this case, we want a force that's going to repulse that part of the robot. So that point on the robot corresponding to the collision of the center of the collision sphere, we want to repulse that away from the obstacle. And likewise, the target is going to be pulled towards a target that might be in three-dimensional space, or it might be given by translation and orientation. And so we have these spaces of different dimensionality, but ultimately we have to get back to the configuration space of the robot, the joint space of the robot. And there's a nice language for doing that using the formalism of differential geometry and specifically Riemannian geometry. Okay, so that's where the term Riemannian comes from. You can look at the papers. At the end of the day, it's not that complicated. It's taking Jacobians and transforming these forces back to the joint space of the robot. Along with the forces themselves, there are also matrices. They can think kind of like mass matrices in the language of differential geometry. You could also consider them to be metrics if you're familiar with that term. That's as deep as I want to go. But as we look at the documentation and at the configuration files that RMP flow requires, you're going to see these you're going to see the term metric appear there. So I wanted to mention it. Okay, let's see. Okay, there's a question. Zia Ideas asks, is that should be RMP, is RMP specifically for joints? So RMP, what it's producing is an output, an action, and at least for robotics, generally we're thinking about joints, whether they're prismatic or revolute joints. That action is going to apply at the joint level. As I mentioned, RMP produces accelerations at the joints. Then we integrate those. You could imagine, doing torque control of the robot directly, but often you integrate those forward to get velocity and position. So I hope that answered the question. Let me know if not. There's also a question. Oh, I see. This is sort of the second half of the question. Or could we also apply it to solve a target path for drones or rovers? Yes, you could do that. That wouldn't be crazy. So a joint, a free point in space, you could think of that has X, Y, and Z degrees of freedom, plus maybe rotational degrees of freedom. You could, in fact, take those X, Y, and Z degrees of freedom and treat them in the same way that I was just describing joints, right? You could get acceleration in Cartesian space, and then use that to produce a trajectory. Whether that's the best thing to do is another question, but certainly you could do that. The question on the spelling of Riemannian. Okay, someone already helped out in the chat. What other motion policies are there besides Riemannian? So I believe that this term motion policy and acceleration policy, there certainly have been similar ideas in the literature. I believe Nathan and collaborators sort of originated the term, at least in this context. So in the way that I'm using the term motion policy and acceleration policy, those are somewhat specific to this kind of approach. If you go to this video and search for, you can see what I searched here to find it. This is from an IROS tutorial from last year. So it's going into depth on an evolution of the RMP flow idea called geometric fabrics. That actually steps beyond Riemannian geometry to Finsler geometries, which are sort of a generalization. And it's fair to say that the ideas here have been evolving over the last few years. So in some sense, an RMP is an example of a geometric geometric fabric. So this whole methodology is called geometric fabrics is the more modern term. So you can Google those terms and find papers and so on, but you don't have to be an expert in the formalism to use these tools in Isaac Sim. Oh, someone's reminding me I'm not sharing my screen. I appreciate that. 1 second. Yep, sorry. So this is I think I was just saying that these are the term. This is what I searched to find this video. If you search Nathan Ratliff, that's Ratliff, you'll have to swim through a sea of links to Nathaniel Ratliff, who is a musician, but eventually you might find this. Okay, great. Okay, so again, I'm hoping most of you saw the live stream with Avi 2 weeks ago. If not, I suggest you go back and watch that one after the stream is over. His is much more hands-on and is taking you through all the steps. I sort of wanted to pick up where he left off in one particular spot. And that is, tell you what, for fun, let me load one of the examples that uses RMP flow. There are a couple here. There's a demo. Let's start with that one, since it's kind of fun to watch. So what I did is I'm in the latest release of Isaac Sim. That's 2022.2.1. Under Isaac examples, there's under demos, Leonardo demo. I apologize for the font size. I don't know that I can make it bigger in Isaac Sim, unfortunately. I'm clicking create scenario, which will take a minute to load the assets. As that's loading, I will say that although this is a fun example to watch, is not one that I would recommend looking at in terms of the implementation. So this demo was added 4 years ago. Under the hood, it's using a deprecated extension called motion planning that's actually going away in our next release. It's going away because we now have the motion generation extension with a full set of Python interfaces, and it's just all a lot nicer. Motion planning was implemented in C++ and exposed a much smaller interface through Python. So I'm going to start the timeline playing and then start the task. Okay, you can sort of ignore these orange these orange ghost robots. I'll come back to what those are. Those were added sort of visualization to give the idea that in some sense the robot is considering alternative paths. In the case of RMP flow, it's not actually doing that in a literal way, so it's a bit of a I guess marketing device sort of. So what I'm moving around now is an obstacle, and what you'll notice is the robot is, eagerly trying to do this task of stacking up some blocks, but I keep getting in the way. And the key thing is it's not slamming into the robot, right? So this isn't physics that's moving the robot out of the way. It's sort of a repulsive field that's a result of an obstacle avoidance RMP running. So I mentioned that there are all of these different these different forces acting on the robot at one time. In general, we refer to those different RMP terms as RMPs. So you'll hear me talk about a target RMP that's moving the end effector towards a target, or an obstacle avoidance RMP. So there can be any number of RMPs. You sum up all the contributions. You do some math involving the sum of the metrics, which I mentioned, and that gives you that gives you a final desired trajectory for the robot. All right, it appears to have frozen. Let me stop the timeline. Okay, the ghost robots are given some weird Z fighting. Okay, let's see, any questions about this? Okay, question. This is unrelated to RMP, but I can answer it quickly. This is coming from Twitch. The question is, when will Lula's RRT implementation support orientation targets, and are there any alternatives? The answer is it is being worked on. I'm not sure it will be there in our next release, but we know it's missing. I apologize for that. In general, I should say I mentioned the various motion generation algorithms that exist in Isaac Sim. Isaac Sim, like all of Omniverse, is a platform. It's really meant for developers like you to take, to extend, to connect to other technologies, to other products. It's not meant to be an application by itself. And so in that spirit, we provide some motion generation tools out of the box, but we also provide, for example, a example of how to connect Move It to Isaac Sim via the Ross bridge. And I think there are some nice tutorials online by Picnic, which is the company with a lot of the core Move It developers. They did a nice tutorial for how to use Move It together with Isaac Sim. There are other third parties that are working on attaching their own motion generation tools to Isaac Sim, and there's nothing to stop you, if you have your favorite tool, from incorporating it into Isaac Sim. The motion generation interface provides these out-of-the-box implementations, but it's also meant to provide a set of interfaces. So there's a motion policy interface where if you have a controller or a planner that could be described as a motion policy, then you can hook it up in the exact same way that RMP Flow is hooked up. We also, by the way, do have geometric fabrics in Isaac Sim. I don't think it's hooked up in any examples. I can talk a little bit more about why not. So, okay, hopefully that answered that question. Okay, let me clear here. Let's start a new stage. Okay, and I'm going to load another simpler example. Under the manipulation submenu, there is a follow target example. Okay, this is a similar story. In this case, the red block is a target. And in a moment, I'll add an obstacle. So again, I can start the timeline playing, click start to follow target. Okay, and you'll see the target turns green when it's been reached. I can slide it around. And add an obstacle. And it hit the robot. That's kind of rude. So what I'm going to do with this obstacle in the property pane, so you can see obstacle cube is selected. I am going to disable gravity so I can place it anywhere in space I would like. So in the physics property pane, there's a checkbox for disable gravity. And once I do that, I can lift the block up in the air. It's still physical, so it'll still hit the robot if I slam it into the robot, but it's not being pulled down by gravity. And I don't know if you can tell, the video quality is good enough to tell, but the robot is sort of gently moving away without me actually touching it as I slide the obstacle towards the robot. That one, okay, yeah, it's moving a little bit. Let me change the angle. In any case, you get the idea. Okay, so let's talk briefly about the files that are required to get RMP Flow working. Again, for the extended version, go back to the live stream 2 weeks ago, to Avi's live stream. So here in VS Code, I've opened up, I'll hover over so you can maybe see the path. So tell you what, let me show you a trick real quick in case you don't know. If you go to the help menu in Isaac Sim, just above about, there is Isaac Sim app selector, which pulls up the original app selector that if you launch Isaac Sim from the Omniverse launcher, this is usually where you start. And you can see the package path here, and you can click open in terminal to get a terminal, and then see where that lives on your system. So I've navigated that place in VS Code, and if you look to the pane at the pane on the left, you can see 3 files. There's a URDF, so this is a standard ROS URDF, in this case for the Franca. There is a robot description file, and Avi went in depth about how to create one of these files. There is a tool in Isaac Sim for doing this. it basically describes, you can see it basically augments the URDF. So it contains some of the same information as the URDF, but it goes a bit further in specifying which subset of joints from the URDF constitute the C space of the robot, because there may be other joints that aren't controlled. Let's say the fingers of the gripper, maybe you don't want to control with RMP flow. There's a set of acceleration limits, jerk limits. Those would be used by the trajectory generator. They're not actually used by RMP flow, but this is a common file that's used by several of our motion generation tools. And then one thing that RMP flow does need, if you want it to do collision avoidance, is this collision sphere representation that I mentioned. So this is a list of the robot links, each with some number of collision spheres attached. So again, there's a visual tool to help you author these collision spheres. So you can do it by hand, or you can attempt to auto-generate the spheres. Often the ones that are done by hand are a little bit nicer if you take the time to do that. So that's it for the robot description file. You pause for questions. Okay. Question: is there a collision field on the cube, a cube or a sphere like we saw with Avi? Yes. So what's happening is that cube is registered as an obstacle. As I go, I should be telling you some of the limitations of RMP flow in the interest of full disclosure. And one of them is that the world representation. So Renan says Lula is great. Trying to get it into OIGE is tough. Yep, sorry about that. We should probably discuss that offline. Lula is the library that most of these motion generation algorithms I've mentioned are that's sort of the one home for these various algorithms. So the IK solver I mentioned, the trajectory generator, RMP flow, RRT, which is a global planner that was asked about previously. Those are all implemented in a highly optimized C++ library called Lula. As of now, that library is shipped only with IsaacSim. So everything in Lula is exposed. We have a public interface with a full set of Python bindings. So as part of the IsaacSim documentation, you can find, let's see, I would have to go to the API docs. Let me try to find them here. IsaacSim API. And if I search for Lula, oh, here it is here. Right, so Lula is this library at the heart of IsaacSim that includes all of these various implementations. They all use the same robot description file. They all currently use a URDF. I realize that might be a little bit annoying since most things in IsaacSim and in Omniverse generally just need a USD. In principle, we could get the kinematic information we need from the USD. We are going to be working on that, so stay tuned. But for now, you do need a URDF for all of these algorithms. You also need a robot description file. And then in the case of RMP flow, you need this RMP flow config file. Okay, great. So, okay, so that was the robot description file. Now let's look at the RMP flow config. And this might be a little overwhelming at first glance. I'm going to scroll down, and you can see that there are roughly 70 parameters or so here. And so this is a YAML file. If you look in the section RMP flow params or RMP params. Oh, by the way, I keep saying RMP flow. I should say that RMP flow is just a framework for taking the various RMPs and it's a framework for summing the contributions together into one final motion policy. That's all that's meant by RMP flow. So RMP flow is what to search for if you're looking for that original paper. So in this section, you will see parameters for each of the various RMPs. So there's one for moving the robot to a desired posture. So this is a C-space target RMP. So in other words, you specify a desired joint configuration, and the robot This RMP is pulling the robot into that default configuration. Often it's nice to, this can be done procedurally in code. You can specify the desired CSpace config. And often it's nice to choose one that's sort of in a natural, resting pose for the robot. And that if the robot isn't active, so in the case of a 7DOF robot, let's say like the Franca, there's an additional degree of freedom, and so having a CSpace target tends to bias the robot into that natural resting posture. This trajectory RMP isn't really used. This is one of the first config files we added, so you can probably ignore that one. Tell you what, maybe I should open up a slightly more modern one. Let's see what we have for the Denso. Okay. So there's again, the affine RMP tends not to be used very much. The joint limit RMP, this is limiting the positions of the joints. There's one for limiting the velocities at the joints, so the joint velocities. There's another for driving the end effector to a target, and this is a position target. So this one cares only about translation. And then there's also an axis target RMP. The way this is handled currently in RMP flow is what this is actually doing is it's attempting to align the X, Y, and Z axes of the end effector frame to the desired target frame that you specify in code. There's a collision RMP for avoiding collisions with obstacles in the world. Oops. And let me hop back there. And then there's a separate damping RMP. There's also some damping built into one of the other RMPs above. There's an additional damping RMP if you observe that you're getting oscillations or jerk that's higher than you'd like. I will return to this question about cubes on collision field on the cube. I'm sorry, I realized I kind of got on a tangent, but we'll get back there in a second. In addition, I mentioned as we were watching the Yumi video that at the moment, the collision spheres on the robot arm are not used for self-collision avoidance. That's handled separately, and it's handled through what's sort of a hack, but it turns out to work pretty well in practice. The idea here is that you add a single, you add one or more cylinders, which are actually capsules. So they're places where this terminology hasn't been cleaned up. The cylinder here means a cylinder with two hemisphere end caps. So that's typically called a capsule in like the physics simulation literature, in the control literature. So you specify one or more cylinders that the robot should avoid, and then separately specify these collision controllers that you place. Often it's good enough just to put one or two on the end effector. That combined with the fact that the robot has joint limits that the manufacturer specifies to avoid self-collision between neighboring links. The combination of these two things in practice does pretty good at avoiding self-collision. But if you have a robot with multiple arms, or let's say a composite robot that you've built out of let's say two separate arms, then that's calling out for a better solution for self-collision avoidance, and we don't really provide that today. You could make it work yourself by, let's say you have two arms and you want one to avoid the other arm. You could attach spheres, let's say, or cubes or some other primitive capsules to that second robot, and have the first arm explicitly avoid collision with the other arm, and vice versa. It's a bit awkward to do today. We are going to be working on tooling to make that easier. So in the meantime, I apologize. Okay, so let's go back real quick to this question. Is the collision field on the cube, like we saw with Avi? So the way that the world is represented for RMP flow, as well as for example, the global planner that's in Lua and exposed in Isaac Sim, the world is represented as a set of primitive shapes. So those are boxes, or if you could call them cubes or cuboids or rectangular prisms, right? But just boxes of any dimension, capsules, which I mentioned, and spheres. So today it's necessary to, by hand, author. If you have obstacles in the world, you basically have to hand place those primitive shapes and scale them in the right way. If the obstacles are going to be moving, you just ensure they're attached so that as the object moves on the stage, Lula's world is appropriately updated. That's the way the environment is represented. We're working on going beyond that, but today that's the way it works. Okay, I haven't seen a question for a while. Feel free to ask questions. I'm always happy to pause and answer any that you guys have. Okay. I should have, so this is the file. I wanted you to see what the files look like. The good news is, in general, you don't have to create one of these RMP flow config files from scratch. Typically, what we do is take one for an existing robot. Often it works right out of the box, and if not, we modify it. The one thing you may want to pay attention to, so two of the robots we have are the Franca. This is the white robot that I was showing in the two Isaac Sim examples a moment ago. Franca is a 7 DOF robot. And so if your robot has 7 degrees of freedom, this might be a good one to start with. If you have a 6 DOF robot, maybe pick up the RMP flow config file for the UR10. So this is a UR10 from Universal Robots. We have other examples in Isaac Sim for the UR10. So for example, let me load one of these other demos, which is a palletizing demo. All right. This is taking its time loading. Oh, do you know what? It may be a problem. I didn't close the previous. All right, tell you what, this is bogging down my machine, so I'm going to force quit. I could have been patient, but okay, so we'll let this load. Okay, in the meantime, let's see, questions. Okay, if we were to model a robot for SimReady, do we need to consider making the collision, or can the collisions only be determined in URDF? Okay, so if you have a robot, ultimately everything in Omniverse is USD. So you never need a configuration file besides that USD if you have your own way to control the robot. If you are using the motion generation algorithms that we provide with Isaac Sim, at a minimum, you will need a URDF. And in fact, you will also need the robot description file that I mentioned. If you're using a third-party package such as MoveIt, you probably will also need a URDF. So, in general, you're going to want a URDF. Ideally, we would have a USD to URDF converter. We're working on it. Stay tuned. I can't give a timeline for that. I'm sorry, but you do need a URDF for your robot. If you're using these various Lula algorithms, you also need a robot description file. And then if you want to avoid collisions, either by planning a path offline using the global planner in Lula or using RMP flow, you do need the collision spheres I mentioned. Those also live in the robot description file, just as a list of spheres. And I could show you how to produce a robot description file, but I'll suggest you hop back to the live stream from 2 weeks ago. That's linked in the chat. And you can skim through Avi's live stream to get to the point where you see him adding big yellow spheres to a robot. That's the part you want to watch. And that goes through the process of adding these collision spheres. I'm going to assume that that's what was meant by the question, but let me know if not. Okay, so I was, you can do this on your own, actually. So for fun, if you have Isaac Sim installed, feel free to load up the UR10 palletizing example. This is a UR10 from Universal Robots with a conveyor belt and some purple bins that where the task is to stack those bins. Again, these demos are not the best examples to look at for how to do this with your own robot. Best practice would be to do what Avi did 2 weeks ago, use the extension template generator, and I think at least one of the templates is already basically wired up to use RMP flow. Avi also talked a bit about gain tuning, which often comes up, right? So if you have a robot, tell you what, since I'm going to be rambling anyway, let me load this and we can watch it while I ramble. If you have a robot and it's not doing what you expect, there are a couple possibilities there. One is that actually you do have to tweak the RMP flow config file to get better behavior. But another is that might be that the simulated robot isn't following the trajectory that's being produced by RMP flow. And if that's the case, there are a couple tips for debugging in the RMP flow tutorial, which I can bring up since this is taking a long time. So let's see. So yeah, I do want to advertise, by the way, we do have a very nice set of tutorials that walk you through adding a robot, getting RMP flow working on a robot, as well as we don't have one yet for the trajectory generator. I think we should. We'll do that soon. And then separate from the tutorials, there is this manual page for the motion generation extension. And if you search, if you just Google for RMP flow tuning guide, it should bring you to this page. Indeed, it does. Right, there's a tuning guide, and then above that, there's the general manual for RMP flow. So as we were walking through that config file and I was waving my hands around, it may have been actually better to come here where all of the math for the various RMPs are laid out, as well as the parameters and what they mean. I mentioned that often you don't have to worry about these in detail unless something is going wrong. If you have a new robot and you started by copying one of the existing RMP flow config files, one thing to pay attention to is that the UR10, I forget the reach of that robot, but it's a meter or so. If you're attempting to use RMP flow with a big industrial arm, let's say, that robot is at a different scale. And you'll notice that some of the parameters in these tables have units. Many are dimensionless, but some have units of meters. And so in that case, you may want to rescale the corresponding parameters to sort of match the scale of the robot. If you ever do want to start totally from scratch, that's where the RMP flow tuning guide comes in. It takes you through this process of starting with almost a blank slate. You'll probably still want to copy one of the existing files and comment out most of the RMPs. Go through this process where you start with just the C-space target RMP that's defining sort of a default posture for the robot. Then enable a target RMP. And this gives you some tips for how to go step by step to get a working RMP flow config file. Most of the time you wouldn't have to do this. It's enough to start from one that's for an existing robot and just modify it as needed. But just so everyone knows that this is available. Okay, so we're low on questions. Let's see, we have 10 minutes left. I would like to open it up. If anyone has questions in general about motion generation, about manipulation, I might even be able to help with legged locomotion. If you have questions there, or just general questions about Isaac Sim, feel free to post them in the chat. Okay, trying to decide what's the next most useful thing to do. I don't think it would be worth me going through this process. It would be a bit tedious and a lot of me just editing text files. But if anyone tries this and has trouble, please, forums are always like sort of the first best place to go. Partly because you may find that your question is already answered. And if not, once your question is answered, either by one of us, one of the Isaac Sim developers, or by the community, it's there to be found by everyone else in the world. So I would like to publicly thank anyone that has ever answered a question on the Isaac Sim forums or the Omniverse forums. It's honestly a very useful service. Everyone on the team, we do our best to answer questions as quickly as we can, but we are always balancing that with actually improving the product. So thank you to anyone who's ever answered a question there. There's also Discord, which I feel like this live stream audience, that many of you are on Discord. I think I recognize at least one or two of the avatars. Okay, we have a question. How would we go about applying RL to the robots learning? Okay, the short answer is Google Isaac Gym. And maybe I'll type documentation. Well, I'll take you to the page here. Okay, actually, this is not what you want to use. So Isaac Gym is a little confusing. There may be folks watching the stream who have used Isaac Gym in the past. Isaac Gym has existed for 5 years, I'd say, 4 or 5 years. For most of its life, it was a standalone application, and it was available as a preview release. So the standalone application was never meant to be the final product. It was a preview release, so people could experiment, get a taste of the power of GPU computing for this application. What makes Isaac Gym special is that, obviously the rendering is done on the GPU, but the physics is also done on the GPU. Not only that, but it's a framework for performing reward and observation calculations in RL, full end-to-end GPU pipeline, which means it's very fast. The preview release still exists. You can still download it, but the modern way to use Isaac Gym is as part of the, let me see if I type Isaac Sim Gym. It is an extension within Isaac Sim. I think we have to work on our SEO. That's pretty sad. Let me see if I can just find Gym on this page. Okay, so there's a whole section under main extensions. This is in the API documentation. In the main documentation, there's a whole section of tutorials for Isaac Gym. Okay, so this is an extension. It's now fully part of Isaac Sim, part of Omniverse. Much of the same underlying technology as was in the standalone Gym implementation, but it all lives within Isaac Sim. There are lots of examples. There is a separate Omni Isaac Gym EMS. I think Renan might have mentioned this repo. This is an open source repo of examples, and let me zoom in a bit. You can see some of them here. RL training environments, all provided out of the box, that can be used with the Gym extension. So my advice for getting started would be to probably start with some of the RL tutorials that are part of the Isaac Sim. Where'd that go? Well, anyway, part of the RL tutorials that are within the Isaac Sim documentation, and then maybe also check out OIGE, Omni Isaac Gym EMS. Okay. There, you may also find an Isaac Gym EMS GitHub repo. That was for the older standalone Isaac Gym, the preview release of Isaac Gym. Okay. Okay, there's a question. Is it helpful to 3D model our own custom robot arms? it depends what you want to do. I mean, in general, I think for Isaac Sim to be most useful, you're going to need some visual representation. It doesn't have to be, the highest visual fidelity. You'll notice if you, let's say, search YouTube for Isaac Sim, you can find many videos that are photoreal, where we're doing photoreal rendering of the robots, of the environment, whether it be a warehouse or a factory. And that photorealism, obviously, it's useful for giving an idea of what an actual environment looks like. But one of the main use cases for Isaac Sim is sensor simulation. And so photoreal rendering is also really useful if you have a camera or even a depth camera and you want to get photoreal sensor data, let's say for feeding into a perception system, right? Where you're going to be developing or testing or training an end-to-end system in Isaac Sim. That photorealism is really useful. Now, and that might be a reason that if you have CAD for your robot, to import the CAD, there are various ways to do that. We could make that a separate live stream. Or maybe Renato has already covered it in a past live stream. I'm not sure, but there are importers for CAD and also connectors to various content creation tools, right? So you could use an importer from SolidWorks, or you could mock up your meshes in Blender and bring them in that way, or use Onshape. So Onshape is an online CAD package that has native support in Isaac Sim. So many people find it convenient to, even if they have CAD, even if the CAD wasn't originally authored in Onshape, it can be useful to bring it into Onshape as a way to get it into Isaac Sim. So full fidelity is great, but if you want to build a robot out of rectangular prisms and cylinders and just make it look good enough, so you can test out some motion generation or some other part of your workflow, you can absolutely do that too. Okay, friendly for deformable. There's a question. Is it friendly for deformable terrain for RL training? Deformable. Okay, so there are, I would say, okay, so PhysX, which is part of Omniverse, does support soft bodies. We do not currently provide much in the way of examples of soft bodies. In the chat, I think Raynon mentioned Orbit, which is another collection of environments and some interfaces for using those environments. I believe there may be some soft body examples there, but in general, I haven't seen anyone yet produce an actual deformable terrain. So that would be like if you had a legged robot that was jumping from a couch to another sofa or something. You might want deformable bodies for that use case. I think we will be providing more in the way of examples of manipulating deformable bodies in the future. That particular deformable terrain, I don't see why it couldn't be done, but we don't have examples at the moment. Okay, question, what is OIGE? Should I use that? Hopefully that question was answered. If you're interested in doing RL training, reinforcement learning training, take a look at OIGE for examples. Alrighty. Okay, there's this question about self-collision. I did address it briefly earlier in the live stream. The answer is we don't have a great way to do that today. If you missed that part of the stream, rewind to where I talked about collisions. Body cylinders, I think, is the term that we use. If you have a single arm and you just want to avoid self-collision, so let's say a single serial robot avoiding collision with its own base, you can use that body cylinder mechanism to avoid those collisions. If instead you have, let's say, multiple robot arms that are in close enough proximity that they might interfere or collide with each other, out of the box, we don't provide a nice way to do that. You could attach primitives, let's say capsules, to each of the two robots and register them with the Lula world of the other robot, and so that they know to avoid each other. But you would have to do that on your own, and there might be a bit of a performance hit because all of that is going back and forth to USD. There are ways to make that faster, and in the future, we're hoping to provide better out-of-the-box support. Another limitation currently, RMP flow, the implementation that's in Isaac Sim only knows about a single end effector frame. So, that control frame, by the way, doesn't have to be at the end effector. You can put it anywhere, but only a single target frame is supported, which means if you have two arms, because in general you're going to be navigating to a different pose for each of the two arms, you'll have to treat them as two separate robots. So set them up as two separate robots. They can share a single Lula world, but yeah, it's going to be, well, they can share copies of the same Lula world. I'll say that. Sorry, it's a little bit awkward currently. Okay. Okay, there's a question. Adding one or more high-resolution cameras to the world will slow down the simulation a lot. Is there any way to avoid that? I'm not the expert on this. We should have someone in a future stream who is an expert. I will say that there are a couple different mechanisms for using cameras in Isaac Sim. I believe that one of them is to use the ROS. There's a ROS publisher for camera data. That one, believe it or not, is actually more efficient, I think, than using the built-in camera extension. And the reason is currently under the hood, that camera extension is using a lot of the machinery that was built for Replicator, which is our synthetic data generation tool. So there's some overhead there. I'd be interested to know, what approach you're taking for. Maybe you're saying you're just opening multiple viewports with multiple cameras. It really depends on the use case, but I'll make a note. We'll try to cover that in a future stream. Okay, we are at the hour, and I see some additional questions, but I'm going to suggest we take those. We take those to Discord, where we can also loop in some other experts. In general, I tend not to be on Discord very often, but I will try to join later today after the stream in case there are any lingering questions. Again, for general questions, if you're having a specific problem in Isaac Sim, I'd always suggest asking on the forums. But there are some useful or some very helpful community members who hang out on Discord. Some of them are in the stream, and yeah, you can always try Discord as well. But if it's something where you think you might need help from the Isaac Sim team, I would say forums are the way to go in general. Thank you all so much for joining. I think I'm going to end it here. And if you have suggestions for future streams, post them on Discord. That is a good place for that. And we will try to find an Isaac Sim developer to cover those topics. Okay. Have a great day, everyone. Thank you.